This talk presents Depth in Space, a self-supervised deep learning model for estimating 3D depths from structured light sensors. Structured light sensors consist of an infrared projector and camera. The projector projects a random but known dot pattern texturing the scene, while the camera captures the projected dots along with the passive ambient light in the environment. A depth estimation method can predict a disparity map for each image based on how the captured dot pattern is deformed compared to the reference dot pattern. Depth in space includes three different but connected models. We first propose a self-supervised training scheme for single-frame depth estimation. We then extend the model architecture to fuse the data of multiple video frames to obtain more precise disparity maps. Lastly, once the multi-frame model is trained, we exploit the resulting fused disparity maps as pseudo-ground truth to fine-tune the single-frame depth estimation network. Here you can see the training scheme and loss functions for a pair of video frames, I and J, from the same scene. The disparities are individually estimated from dot images via DispNet model architecture. The predicted disparities are used to impose photometric consistency between the reference pattern, P, and the input frames. We also incorporate an edge-based smoothness loss function that encourages the network to produce smooth disparity maps. Finally, we impose consistency of the predicted geometry. In this regard, we use the pre-trained light flow net model in the pair of ambient images to estimate the optical flow. Then, using the warping technique, we impose consistency of predicted disparities among all pairs of images from the same scene. To further exploit the data from video frames, we also propose an alternative model, in which we directly fuse the information from different image sources. Our fusion framework uses continuous 3D convolution as its key component for fusing the image's data. This figure represents our fusion block when we fuse a feature map of frame J into a feature map of frame I. Thanks to the estimated imperfect disparities from our single frame model, each feature can be back projected to the space and be associated with a 3D point. With continuous 3D convolution, all points from different image sources can be convolved together and exchange information, resulting in fused feature maps. In parallel, we also incorporate two-level conventional CNNs to compensate for the shortcomings of 3D convolution like edge fattening. To be more specific, our 3D convolution follows the same notion of the separable CNN, but it operates in continuous space instead of the fixed 2D grid. For each target point with feature phi and location x, we first search for the nearest neighbors. For all nearest neighbors, we calculate the vector that starts from the target point and ends at the neighbor's location. We pass these vectors to a shared MLP to obtain semantic multiplication weights. The weighted sum operation replaces the depth-wise convolution in the separable CNN. Lastly, using the learnable matrix psi, we resemble the channel-wise convolution. Here is the whole architecture of the multi-frame model. First, each dot image is concatenated with its corresponding ambient image and imperfect disparity map that is estimated from the single frame model. Each frame is then separately processed with a series of convolution layers and residual blocks to produce information-rich feature maps. Then, a cascaded series of 4 fusion blocks is employed to construct a fused feature map for each frame. Lastly, we propose a refining structure and reintroduce the ambient image to the network to further process the features and remove the artifacts originating from the fusion process. A qualitative analysis of our model's performances is presented in this figure. You can see the ground truth disparities, input dot images, predicted disparities from different models, and their corresponding error maps. The samples are from various synthetic and real datasets. Compared to the existing methods, the disparities from the depth in space models, particularly the multi-frame model, are superior at preserving edges and high-resolution details of the scenes. Here we compare the results of our fine-tuned single-frame and multi-frame models with the previous state-of-the-art model, connecting the dots. The video is one of the sequences from the real dataset that we captured and made publicly available. On the top, you see the color-coded disparity maps, and on the bottom, you see the spotlight-rendered videos. Rendering the scenes better contrasts the quality of the generated surfaces and normals in our proposed models. Thanks for listening. For more information about our project, including the code and data, please visit our website.